Okay, now that we can convert data into integers, so we can take an arbitrary key and convert it into an integer using one of our techniques, let's go ahead and take those integers and convert them to a valid location. So we're going to assume that we have a key k and m buckets. Note that this is a slightly different use of the variable k than I had in a previous example. So here k refers to the integer value of the key. What we're doing is sometimes referred to as compression. So to see why, think about the int values versus our m buckets. So if we think about our integers as kind of being a segment of the number line, they go from about -2 billion up to about 2 billion. And if we think about our buckets as being an array, it might be relatively small. It will go from 0 up to n. And we're probably assuming that we have fewer than 4 billion buckets for most examples. So you can kind of think of the entire range of this number line as being squeezed down or compressed into our available buckets. Okay, so we'll look at two major approaches for doing this. There are other approaches besides just these two. So one of them, the simplest, is the division approach. And by division, we really mean the result of division, the modulus or the remainder that we get as a byproduct of doing a division. And we'll also look at the multiplication method. Okay, so the division method, again, we're assuming that our key is k and we've got m buckets. And if we want to find the location of a key in our buckets, that we'll refer to that as I. So the division method is pretty straightforward. You just take the absolute value of the key to assume that we have a positive value and the modulus with our number of buckets. So if you remember, this is the remainder after division. So this will give us a value from 0 up to and including m minus 1, or you could think of it as a value from 0 up to, but not including m. Okay, so this is really straightforward. You just do a modulus with the size of your hash table, the number of buckets or the number of slots you have available in it. So let's go back to an earlier example and look at how this will play out. So we'll go back to our string example. So we'll use this formula to determine the location, and we'll assume that we have a total of 10 buckets. So our m would be 10. And we'll think back to the various string examples that we used earlier. Okay, so let's think back to our strings. So pots, the hash value, the integer value is 3446974. So if we do the remainder of that after dividing by 10, we'll end up with a location of 4. Tops had an integer value, 3566014, and if we do the modulus after dividing by 10, we get 4 again. We had a collision. Ops, oh no, if you remember, all of these end in 4, and because we've got exactly 10 buckets, the modulus will always place all of these in bucket 4. Okay, so the value of m is relatively poor for this data. So our number of buckets just doesn't evenly divide up our data very well using this particular scheme. Now, there is a partial workaround. It doesn't always work. There are still pathological cases where it will fail, but it may work better for this case. So if m happens to be a prime number, there's less of a chance of a problem. Okay, so let's redo this, and this time let's use m that happens to be prime. I'll make it be 13. We've got a total of 13 buckets. Okay, so again, we'll plug in our hash value, we'll do the mod with 13, and our remainder for pots is 11, so it goes in bucket 11. Tops is bucket 10. Oh, no collision, excellent. Ops is 2, again, no collision. And spot is 10. So we did still have a collision, but notice that at least we didn't have 3 collisions. Okay, let's move on and talk about the multiplication method, which is just slightly more complicated. This is fully described in the Corman text, the Introduction to Algorithms textbook that's a recommended reading. So the formula for this, it looks something like this. So I is equal to the floor of m times the quantity k times a mod 1. Okay, so let's break this down to its individual pieces. Again, K is our key, and M is our number of buckets, and we're trying to come up with location I. One other thing that's important here is this parameter A. It's strictly less than 1, but greater than 0. Okay, so it's a fraction, but it's less than 1. And also equally important, it's greater than 0. So the individual pieces of this, the K times A is basically multiplying the key times some sort of a fraction. So this will leave some sort of a smaller value, possibly with a fractional result. It may not be a whole number. So as an example, if the key is 11 and A happens to be 0.1, 0.1 times 11 would be 1.1. So it now has a fractional component. Okay, so then that number gets plugged in and we compute the modulus with 1. Really, this is just notation indicating that we keep the fraction but discard the whole number part. So again, if in our example we had 1.1, we would basically discard everything before the decimal, and we'd end up with just the 0.1, the fractional component. So again, this is, it may be equal to 0, but it will be strictly less than 1. Okay, so then we're going to take that value between 0 and 1, and we're going to multiply it by M, our number of buckets. So if you kind of think about M, again, with one of the little number line pictures, 0 up to, but not including M, and we multiply some fraction by this, basically we're saying how far along this number line we want to go, and then we're going to take the floor of that, which will just give us an integer back. Okay, so we'll convert that fraction. So let's go back to our example using this approach. So again, here's our formula. In our example, we'll again use 10 buckets just like we did before. And for our value of A, we'll choose 0.1. And we will apply this formula to our strings. So pots, again, our hash value is 3446974. If we multiply that by 0.1, basically it's moving the decimal over one place. We can kind of think of it as ending in 0.4. Of course, then if we drop the fractional value, drop the integer value, and multiply this by 10, our location ends up being 4. Oh, this looks kind of familiar. We saw this earlier. So if we repeat this with tops, you can probably guess what will happen. We multiply it by 0.1. We end up with a fractional component there. We drop the whole number. We multiply it by 10. And we end up with an item in bucket 4. We've got a collision again already. And this problem is going to persist with our remaining values. Okay, so this doesn't look very helpful, but there's something that's really important here. We control A and we could change it to something without changing our M. So our earlier approach, the division approach, if we had collisions like this, we actually changed the size of our hash table in order to correct it. Here, we could actually choose a value of A that's more suited to our data, and examples like this where there's some potential for collision. Now, the downside of this is we may have to do some testing and analysis to figure out an appropriate value of A. But the upside is that we've got some additional flexibility that we didn't have before. Okay, so let's redo this problem, but let's use a different value of A, but still 10 buckets. Again, still the same value of M. This time we'll pick A to be 0.72. This was a completely arbitrary choice. Okay, so pots, our hash value, we already know. And when we go through our conversion, it ends up being placed at location 2. Tops ends up being placed at location 0. Ops ends up being placed at location 6. And spot ends up being placed at location 8. Oh, this is great. No collisions whatsoever with this example data. And again, all we had to change was this constant that we're using in our hash process. So, not bad.